Good morning, everyone. Thank you for coming today. My name is Xiaoji Chen. I am the chair of the technical steering committee of vis.gl. On behalf of the steering committee, I would like to welcome you to Open Collaborator Summit of 2023. With my fellow committee members, Ib and Chris, I'm going to take you through the journey vis.gl had in the past year, and we'll give you a sneak peek of what to look forward to in the next major. Just some highlights of all the releases we had in the last year. This is all the frameworks and libraries that's currently in the vis.gl visualization suite. We have the flagship deck.gl for data visualization. Deck.gl depends on a set of lower level libraries that provide different functionalities. We have the framework agnostic file format loaders.gl. We have the WebGL API wrapper, Luma.gl. MathGL provides mathematics and geospatial computation utilities. And ProbeGL offers logging, testing, benchmarking utilities. And on top of DeckGL, we have libraries that extend its functionality for specialized use cases. We have HubbleGL for timeline animation, NebulaGL for map drawing and 3D editing, GraphGL for non-geospatial node edge-based graph visualization, and our latest addition, FlowMapGL. We also have base map wrappers. ReactMapGL is a React wrapper for Mapbox and MapLibre. React Google Maps is our latest member in the suite, and you'll hear talks about that later. I have Kepler.gl, which is more like an application end-to-end no-code user experience, and we have Python bindings for both DeckGL and Kepler. DeckGL in its latest production release 8.9, one of the highlights, Tile 3D layer now supports Google Maps photorealistic 3D tiles. It's really a wonderful data set. It's hyper detailed, great coverage with all the great data that Google has. If you haven't seen it, you can read the announcement blog post and see an example on the DeckGL example page. As the screenshot shows here, we have the all the very detailed 3D models and textures of a city here, and DeckGL can overlay other data sets on top of it. Here, all the buildings are colored by its distance to the nearest tree. And to make that work, we also shipped generic terrain extension. This allows you to render flat geospatial data on top of a terrain source. There are two modes. You have offset mode where you shift a 3D model by its anchor position to the surface of the terrain, or you have drape mode where you render a geometry-like path or polygon as texture along the surface of the terrain. This feature still has an experimental flag, but it really opens up the opportunity for you to collect data from different sources and put them together to create appealing and insightful visualizations. Another new addition is the collision filter extension. This is a GPU-based filter where it dynamically looks at whether data objects overlap on screen and show and hide them accordingly. So here is our text layer example. You can see as the user zoom in and out, it picks the right number of labels to show to maintain the best readability. Over the last year, we also added mask filter extension. This one is also GPU-based. It shows and hide data objects based on whether it lays inside a geofence. The performance is great especially when you have dynamic data or changing geofence, very complicated shape. It really moves the burden of doing expensive geospatial tests from the CPU to the GPU. A few other new features. So we have the new WMS layer, which talks to a WMS server to load raster map imagery based on the viewport that you are currently looking at. We ship the custom tile layer indexing system. So tile layer is no longer bound to the OpenStreetMap scheme. There's a Mapbox overlay, which works with Mapbox and MapLibre, and makes it a lot easier to interleave vis.gl layers with Basecamp. MapLibre is now also supported out of the box, so you don't have to do anything special when you use the scripting interface. The code base has been slowly being converted to TypeScript. I think we're 95% done now, and in the last version, we started offering the official types, so you can opt in by importing from the /typed endpoint. We did a lot of work under the hood on the dev setup of the repo. The build tools have been switched from Webpack 4 to ES Build. Our examples are now using Byte. And we're using a new website system based on Docusaurus. It has much better visual navigation and search capabilities. I'm gonna hand to Ib, who oversees the development of Loaders.gl, to talk about all the exciting things that came to Loaders.
Okay, thanks, Xiaoji. So Loaders.gl is the framework that sits under DeckGL and also Kepler. And the kind of philosophy of Loaders.gl is to create a core module that allows you to work with loader objects. And then we create a growing suite of such loaders and writers for various data formats. We've been doing a bunch of work. We have improvements in 3D tile fetching and parsing. So obviously now that we've had support for 3D tiles for a long time, but now that the Google dataset, the Google 3D tiles are here, the interest in using this has exploded. And so we've discovered a number of optimization opportunities that we're working through. There is a very significant amount of investment into, there's two complementary OGC standards, that's 3D tiles and I3S for big 3D, massive geospatial 3D data. And Loaders.gl supports both of them. There is a very significant contribution from S3 that's been going on for several years together with Action Engine, especially on the I3S side. And so, and the architecture is done in a way where these, whether you use 3D tiles or I3S, it passes into a common representation, and then you can work with those in the DeckGL tile 3D layer. Another big investment coming from contribution coming from S3 and Action Engine is the converters. So if you need to switch, if you want to work and you don't, you haven't really made your choice on whether you want to work with the 3D tile standard or the I3S, Loaders.gl comes with command line tools for converting big data sets. This is an example of I3S Frankfurt, maybe. I mentioned that the idea of Loaders.gl is to have a catalog of loaders, and this has kept growing. So we have a range. We have tabular loaders that allow you to do streaming reads of very large tables. There's image loaders that now include the latest super compressed texture formats like Basis, and the geospatial loaders also keep growing, looking into especially the new cloud optimized geospatial formats. And we have a number of mesh and point cloud loaders. seeing graphs like GLTF and obviously the 3D tiles loaders. We are working on a new version that's close to, hopefully we'll release quite soon, Loaders.gl v4. The big thing here is that we have upgraded the code base to TypeScript, and now we can type all the loaders. So today, when you work with Loaders.gl, you use a loader and you get the data back, but you don't get types on it. And so now the result, which can often be quite complicated, of these loaders will be fully typed in 4.0. So there will be, I think, a transformative experience. We're also looking at when we pass, especially tabular data and meshes and so on, we generate schemas so you can see what the data types of the different columns are in a portable way. We're working on making those serializable so we can send them between workers, for instance, in the main thread. Node v18, version 18 will be supported. Also, node workers are supported now. For i3S and 3D tiles, the Action Engine team has been working on supporting the archive format. So it's possible to store these, potentially gigabyte or terabyte sized massive 3D archives in a single, or tile sets in a single archive file, kind of a zip file, if you will. And Loaders.gl can now read directly from such a single file and kind of extract the subfiles dynamically. We'll also upgrade Apache Arrow to the latest version. It's long overdue.
On the React Map.gl side, the code base is now fully typed, and all the types can be imported. In v7.0, we shipped a new version with reduced footprint, so it's now a very thin wrapper around Mapbox or MapLibre. It doesn't try to remap any of the APIs. It allows you to have a more direct access to what new options or methods that the base map library exposes. And this allows us to be compatible with a lot more third-party plugins without extra work. In 7.1, it's shipped a non-biased support for Mapbox and MapLibre. So before, it was mainly a Mapbox.gl wrapper, and just by the way, we support Mapbox compatible forks such as MapLibre. But as MapLibre grows and diverges from the original code base, we now see the need to actually have special typing and different interface support for MapLibre. So now the import endpoints have been split. We've been talking about spinning out MapLibre wrapper into its own library. It's not urgent or necessary right now, but that could happen in the near future. In the latest release of MapLibre, it's v3, we have contributed reactive hook into the base renderer itself, so we don't have to do a lot of the hacks that we're doing in Mapbox.gl that can potentially reduce bugs and the amount of overhead that we're adding. FlowMap.gl is one of the new additions to the vis.gl suite. It's a set of deck.gl layers that specialize in visualizing mobility in a geospatial context. If you haven't seen it, it's pretty sweet. Go to flowmap.blue, and it has an interface where you can upload your own data and customize it. And we'll have talks later about React Google Maps. It's a fully typed modern React wrapper for Google Maps JavaScript API, and it works out of the box with the React version of deck.gl, just like React Map.gl, which is really, really great news for us. We have a wonderful growing community. Thank you all for being part of it. We have we now belong to the OpenJS Foundation, which is an part of the Linux Foundation, and we have a growing number of companies that are sponsoring or directly contributing code to the vis.gl suite. Some numbers, vis.gl weekly downloads. I looked this up last week. Was at 178K per week, up from 100 a year ago. React Map.gl weekly downloads is at 344. We've had 27 community meetings. This is all open from the OpenJS Slack and repositories. You can freely join. And we have archives and documentation of all the past meetings, of things we discussed, what we are doing, and where we're going next. We've had almost 900 PRs from over 100 unique users, and even more community members participating in reporting issues and discussing the usage. And these are all wonderful contributions that help us understand what you guys are using it for and how we can do better. We have a new website for the OpenJS Open Visualization workstream. Yeah, this is at openvisualization.org. You can go check it out. And the more exciting topic is what is happening in the next major release of vis.gl. Let's first talk about Luma. Luma v9 is almost a complete rewrite. We are trying to add web GPU support. So if you remember, the vis.gl tagline is WebGL 2 powered large data visualization in the web. Soon that will not be accurate. And we are embracing the successor of WebGL, that is WebGPU. It has become generally available in the last few months. Chrome and by extension Edge has flipped the switch and made it by default enabled in May. So that covers about 26% of web users that can use the web GPU rendering engine without any work. In Firefox, it's available in nightly build. Safari used to have it enabled in developer preview. That was even before they added WebGL 2 support. It's a metal-based implementation, but I think they disabled it since because of the spec change. The web GPU specification had been had a lot of instability because of the disagreement from the participating members in that discussion up till I think last year. But now it's officially shipped in Chrome. We expect it to be stable and expect the other major browsers to catch up in the next year or two. So probably what you are most interested in is what will web GPU technology bring to the data visualization world. Just a few points. Web GPU is supposed to bring better performance because of the way it handles commands. In WebGL, everything is a single function call. Every time you set a uniform, which we have probably over 100 in a typical layer, it is an API call. In Web GPU, there's a command buffer. You set up a bunch of things, and it's issued and executed in a batch. And this theoretically can help us draw more layers, each one with more complex meshes, or update it dynamically from live source at a higher frame per second. We don't have any benchmark of our own right now, but from what Babylon.js reports for some of the more gaming-oriented scenes, they have seen 10 times the performance gain from switching to WebGL to WebGPU. Web GPU has a new powerful compute shader. So in WebGL, everything is rendering. Is purposed for rendering. Everything ends up being a pixel in a texture frame buffer. And for us to do any GPU-based computation or aggregation, we need to pack and unpack inputs and outputs into textures. And that is really awkward when your data doesn't really match that format, and you're restricted by the pixel format that your texture supports. But in WebGPU, it has a more flexible programming model that allow free memory access, and it opens up opportunity for all sorts of crazy effects and data processing capabilities. WebGPU is designed to, based on a bunch of more modern GPU interface, such as Direct3D, Metal, and Vulkan. And when we support web GPU, it theoretically makes it easier to port rendering logic from web to native platforms. DeckGL Native is an experimental proof of concept repository that we've done to test doing DeckGL rendering on the desktop, and it uses Dawn, which is a native implementation of web GPU. And when we do interleaving layers with either Mapbox or MapLibre or Google Maps, a lot of the bugs or issues stem from the context handoff, because all the WebGL states are global. And when we allow the base map to draw into that context and get it back from the base map, the states have changed without any documentation. So a lot of that unexpectedly changed the behavior of DeckGL, and that's the source of, I want to say 80% of the bugs that get reported to us. WebGL reduces the amount of global states that the context itself holds, and that makes it possible to create more robust and composable libraries. So we could expect to see actually being used side by side with other GPU renderers a lot easier. So in order for us to transition from a WebGL2 renderer to a WebGPU compatible renderer, there are a bunch of API changes coming to LumaGL. Most notably, Luma now has a more WebGPU-like API where it uses adapters and devices instead of legacy classes like texture and buffer. So you do render pass, you do device create buffer and create texture. And Luma has built device implementations for both WebGPU and WebGL. So now, as a user, you don't have to think of whether the client side is using WebGL or supports WebGPU at all. You write the same code, and it will choose the best rendering layer for you under the hood. And when we move to the deck layer, you can optionally opt in to enable WebGPU support. That will add a bunch of add some code to your application, but that under the hood will choose, for example, WebGPU if it's available, and fall back to WebGL when needed. And on top of that, you just write all the layers and stuff the same way you do today. If you're a custom layer author, that will mean some of the resource creation, like texture and buffer, will change inside the layer code because now we are using device instead of GL, and we're moving the shader code from ES100 for most layers to 300 or WGSL. But aside of that, most things in deck will work very similar to what it does today. We have also been exploring interop DeckGL with other GPU solutions. We recently checked in an example that have DeckGL share the WebGL context with TensorFlow.js into the main branch. That's the screen capture top right corner there. It basically uses TensorFlow for a lot of data aggregation and processing, and then hand that directly back to DeckGL without reading it out from the GPU and directly render it to screen. You will hear it from Paul there later today about using DeckGL and CUDA together, again, sharing memory between the renderer and the GPU, and let GPU do the heavy lifting of data processing. Our current plan for web GPU support, Luma 9.0 alpha is currently available. It's still under heavy development, so APIs are expected to change, and certain things are expected to not work. We are currently aiming for later this year to release the stable version of v9.0 for Luma. DeckGL master branch is already upgraded to v9 to use the device API. In the next major release later this year, together with Luma, DeckGL will aim to have the same level of WebGL support as 8.9. So it's mostly going to be not noticeable for most applications, but that represents a significant amount of code change under the hood, and that will allow us to move to web GPU faster. After that, DeckGL 9.1 aiming early 2024. We're going to have full web GPU support in all layers, and from 9.2 and beyond, we're expecting to add new features, especially in GPU-based extensions and aggregation layers that may be web GPU only or significantly more performant when you're using the web GPU renderer. Another major area of work in DeckGL v9 is widgets. So up till now, DeckGL has been mostly about rendering into a canvas. We have said we're not in the business of doing UI, but that sentiment have changed slightly over the last few years. We see applications that require HTML-based UI components and user interaction. Just give you a few examples, like navigation control, where you can control the zoom and pitch of a map, or legends that show you the scale of the current map or the color scale of the current layer you're looking at, and timeline that give you a slider, basically, that you can select either a point in time or a range of time to filter your data. These sort of things are pretty common, and while most users are surely capable of implementing them themselves, it's not really easy to implement them well. And historically, DeckGL has been directing users to use React MapGL for a lot of these components. The issue is when you're not doing a geospatial visualization or you're not using Mapbox as a base map library, it feels really stupid to import this whole big thing just for a React component. And you can see the widgets module RFC checked into the main branch, and I'll have Chris talk about the current development progress.
Thanks, Xiaoji. So with widgets, we're taking a quick look at all the different kind of widgets that are out there, what people need, what they're looking for, and trying to come up with a design system that can meet the needs of what you might need in your application to use widgets. You know, traditionally, since these widgets are HTML and CSS, most of the time you can just put a few classes on all your different widgets, and that was enough. But these days, there are there are so many different design systems out there, so many different unique needs depending on what your needs are within it, that we were thinking about how we could create a few set of core widgets that do navigation. Here we have like zoom buttons, geolocate. So if you click them, it'll zoom the map to your location, put a marker on there, show you where you're at, and basic things like full screen. Those are the things that today React Map.gl and other widget libraries do provide. But with Deck, we can go so much further than just these basic components. And so on the next slide, you can see we're looking at a variety of concepts, like Xiaoji mentioned, around legends and kind of data-based widgets. And we'll have a discussion, I believe, at some point over the next day or two about these. But at a high level, we've been thinking about a few design principles to follow on this so that it'll work well for your application. We felt it had to be very lightweight. It has to be tree shakeable. When, like Xiaoji mentioned, you don't want to bring in a giant library like React Map.gl just for a couple small components, and especially if you're not using these things like Mapbox or React. And so we're looking for a pretty minimal dependency system. Just add a few kilobytes to your back bundle in order to get started with this. But at the same time, it should work well. It should work out of the box. It should have a design system that is extensible, flexible. It should feel like it's intuitive to use, because at the end of the day, this will be used by users. Unlike these highly customizable layers that we provide, where a lot of the work is kind of delegated to the application in order to do the customization. On widgets, you might just use exactly what comes out of the box. And so whatever that is, it should be a good experience. But at the same time, you need it to look and feel like the rest of your application. It'll be on top of your map, but you want it to feel like it's part of the rest of your design system. And so we're going to be taking advantage of newer technologies like CSS variables in order to expose semantic variable names that you can then quickly redefine at the top level of your style sheets and have them cascade down and affect all widgets, and have all those documented so that they're very easy to access and use. Of course, there are classes there as well, so you could do your normal selections and do all kinds of different variations depending on what your needs are. And then finally, it's an extensible interface. So there needs to be infrastructure in place that can support these custom use cases that are unique to your application. The widgets that we're creating are kind of self-contained in the sense that they will, out of the box, work with the Deck.gl object that they're registered to. But if you need to build a custom widget that extends some of the functionality, there's a very clear interface on how you can extend or create your own custom widget and add in additional functionality on top of something. So that would enable things like maybe integration into applications like Kepler that use Redux and other libraries. Instead of directly impacting the Deck instance, they go through, an application might go through a different interface to make that modification. By being able to extend and create a custom widget, you should be able to support these kinds of things. And so this is kind of what using a widget can look like in Deck. So it's a very straightforward system. You can import them from, we're going to be introducing a new Deck.gl widgets module. You can import them from this and then pass them into a Deck widgets prop. At the top, you can see kind of what this looks like in a vanilla JS application. Simply construct your widgets. We have properties on there to help you place them on different parts of your screen. There's also properties in there to do different styling, like see if here you can import a variety of themes. And what these theme objects are is simply a dictionary of CSS variables that have been predefined for you. We have about 4 themes right now that we're just looking to ship out of the box so that you have a variety of different looks to get started with. But of course, you can go in there, change a few of the variables quickly if you just need some modifications and use the rest that comes out of it. And in React, it should work very similarly and feel very natural to use. So we're going to be adding basically wrappers around the vanilla.js widgets that you can import from the React module to just drop in as a bit of JSX. So looking ahead at the roadmap, we are currently in a phase of designing a lot of these widgets and looking for public feedback. Designs are open. On our issues, you can go and check them out. We've got some Figmas up there where you can go and leave comments, and much appreciated on the feedback there. We are looking at kind of an alpha release for 8.10 with some of the core widgets like navigation, full screen, something to get us started there and get it out in the wild for testing. But V9 is where we're really expecting a production release to come out, and we're targeting October for that. With this, we want to get those core widgets really robust. We want to get some nice things out there like zoom, compass, full screen, geolocate, marker, and legend. And legend will be a demonstration, of course, of how you can use the widgets with a few different deck layers where you have different colors or values that you want to show. So that'll be a pretty cool showcase of that capability. And then looking forward ahead, sometime in 2024, it's an ambitious project, but we're looking to rewrite Nebula.gl, which is the vis.gl library for interactive and editable layers. So think editable scatter plots, polygons, things like that. And we're looking to rewrite that as a deck widget. The advantage of that has always been that these layers are native deck layers in Nebula.gl, so you have the performance and everything that comes with that compared to all the typical way of doing it where you do an HTML overlay on top and kind of project it onto your canvas. It's always been an incredibly powerful library, and we're hoping that, but it's been a little tough to use, right, and integrate into applications because it's a separate thing. We're hoping that by designing the widget system to be so easy to use and out of the box support, it'll lower that barrier to entry and help people get started a lot faster. All right.
All right. So so obviously there's a future also for the Loaders.gl library, and one of the areas that I personally find really exciting now is all the work that's going into defining a set of what's called cloud first or cloud native geospatial formats. And we look at some of the kind of members of this category. It's cloud optimized geotip for raster. We have a similar standard for point clouds. It's called cloud optimized point clouds, COPC. There's PM tiles, which is a way to collect basically Mapbox vector tiles in one large single file. There's GeoArrow, GeoParquet, Flat GeoBuff. There's new activity. I see OGC spinning up standardization work on GeoZar. Some of the common properties of these is that they are designed to be serverless. So they leverage typically range requests, HTTP range requests, and which means that you can put very large geospatial data up on. Did I lose? So this means that we can host data directly on static cloud storage, like Amazon S3 or Google Cloud Storage, and without putting a service or a server in front of it. Applications, and especially client-side applications. Obviously, client-side applications can't, like a browser, like DeckGL or Kepler, can't read, a gigabyte or a terabyte of data. So they need to do partial reads. And so all these formats typically then offer you the ability to read an initial index, and then based on that, discover the offsets of various types of data inside of that bigger file format. And so you can do partial data reads directly from these static files. These formats then typically offer, in some cases, geospatially indexed data at multiple levels. So cloud optimized geotips is a good example of that. So they may kind of contain a tile hierarchy inside one big file. And yes, they typically require multiple requests. So it's not as simple as a traditional loader architecture where we pass one URL and loaders.gl loads it possibly in a streaming format. But here you need some code, some class, some proxy that helps you navigate these multiple requests. Now, on the other hand, traditionally, many of the similar functionalities were available through services. And so services, there's two maybe major categories. There's like the OGC, Open Geospatial Consortium services like WMS, Web Map Service, WFS, Web Feature Service, WMTS, Web Map Tile Service, been standardized for a long time. And there's a lot of resources out there that serve data, many kind of institutions, government resources, NASA and so on, provide weather information and other things. Very powerful data. S3's ArcGIS has a set of basically similar services that's maybe a little bit more modern. Cesium has services for 3D tiles and so on and so forth. And in the same vein, working with these services also typically requires doing multiple requests. And as we can see, there's a pattern between these services. Whether you use a WMS service or an ArcGIS map server, what you're basically doing is you're initially asking for some metadata, discovering what information, what layers are there, and then you're asking for images to cover the current viewport. And so you can really create a common interface. The application shouldn't need to deal with the details. And so what's happening in loaders.gl is we're creating a number of kind of abstract services, and then we're providing implementation. So we previously, Xiaoji, explained that there is a new WMS layer in VMS layer in DECGL, and that's then built on top of a WMS service in loaders.gl. Another thing that's I personally think is interesting and we're looking into is catalog services. And so, discovering all these great spatial and spatiotemporal data sets out there can be quite tricky. And so there's a number of different catalogs available in different formats. There's a really interesting format that kind of goes along with the new cloud optimized geospatial format stack, the spatiotemporal asset catalog. And typically, if you're working with the big raster data sets, Landsat and so on Amazon S3, you would need to go through a stack catalog to discover the actual imagery you need to load, the actual cloud optimized GeoTIFF URLs and so on, and some metadata, what bands they contain. But Stack can also describe other types of assets. There is an existing OGC standard called CSW, so it's the OGC catalog service for the web. And if you have an ArcGIS server, if you basically hit the root URL, it will list, provide you with a list of the different services and assets that are available. And so we're experimenting with providing in loaders.gl also the ability to connect to different services and getting back some kind of unified format, a list of all the assets, and then also providing enough information so that you then can automatically select the right loaders or services and so on for accessing that particular data. That's it.
So these were just high-level overviews of what to expect in vis.gl vNext. Most of them you'll be able to either try them or get them in production in the next few months. And throughout today and tomorrow, you will hear deep dives of different points in this slide. If they interest you, we'll have talks about WebGPU, we'll talk about different loaders, about CUDA. We have contributors from Esri and Google who talk about integration with their own formats and services. Enjoy.